Hello everybody and welcome back to another week of DS23 here. This week we're going to go ahead and get started on Chapter 9, and as you may have read, Chapter 9, 10, 11 are by far the most important part of this class. You may have noticed there was a ton of pretty long videos here for Chapter 9. And just so you know, this is definitely the longest week. It won't be that long for the rest of the semester. But the reason why I put so many videos up there is just because it's very important that you understand these concepts. This is basically the part of statistics where if you can understand it, it's just honestly ridiculously easy. But on the other hand, of course, if you don't understand it, it just doesn't make any sense at all. Alright, so I want to get started off with looking at some example problems here. What we're going to do is we're going to start off by looking at 9.1.4, which is number 1 from your 12th homework assignment. It reads, for each of the z-test statistics, compute the p-value assuming that the hypothesis test is one-tailed. And there were parts A, B, and C. But A and B were pretty identical, so we're just going to do parts A and C for this video right now. Before we tackle this problem, let's just remind you guys of what a p-value is. All that the p-value is just the probability of getting a z-test statistic as extreme or more extreme than the one of interest. So, for example, part A, our z-test statistic is 1.42. So in that case, we just want to figure out the probability of getting a z-value that is greater than 1.42. And of course, that correlates with the area to the right of a z-value of 1.42. So I drew out the standard normal distribution right here, and I drew an orange line right at 1.42. And of course, we're interested in finding the area to the right of that, or the area more extreme, aka farther away from the mean or the middle, right? Now, whenever I solve these problems, I always use the standard normal distribution table from the back of your guys' books. There's a lot of tables that might be easier, or you can just basically directly get the answer from, or you can use a calculator too and directly get the answer. But I just use the one from the back of the book just because it's, of course, the one that's definitely available to all of you guys. So let's take a look at this. Well, once again, ultimately, what we want to do is find the area to the right of 1.42. Now, you may recall, sorry, you can barely see this standard normal distribution I have up here. The standard normal distribution in the back of our book gives the area between 0 and a positive z-value. So to solve out this problem right here, basically, since we can only figure out an area between 0 and a positive z-value, what we're going to do is we're going to figure out the area between 0 and 1.42 first, or this area in pink right there. So to do that, of course, we just want to look up 1.42, and that correlates to a value of 0.4222, or 0.4222. So that means this area right here is 0.4222. We're almost done now. Now, of course, remember that the standard normal distribution is symmetric, right? The area underneath the standard normal distribution is 1. So that means the area to the right of 0 is 0.5. The area to the left of 0 is also 0.5. So what we can do is, of course, we can take this whole area, or 0.5, and subtract off the area we don't want, or that 0.4222, and then we'll just be left over with the area of interest. So this area right here is going to be equal to the entire area to the right of 0, which is again 0.5. Subtract out the area between 0 and 1.42, which is that 0.4222. And we come up with an area of 0.0778. Now, of course, the area under the standard normal distribution correlates to the probability, right? So that means the probability of getting a z-value greater than or equal to 1.42 is equal to 0.0778. And once again, we were asked for the p-value, which is the probability of getting a z-value as extreme or more extreme than the one of interest, right? So same thing, z is greater than 1.42, because greater than 1.42 is more extreme or farther away from the mean. All right, next one we want to check out is we want to figure out the p-value, aka the probability of getting a z-value that is more extreme or farther away from the mean than negative 2.25. So I started off by drawing a line right here where z is equal to negative 2.25. But once again, the p-value is the probability of getting a value more extreme. So in this case, we're looking to the right of that. But here, since we have a negative z-value, we're looking for the area to the left of that. Or again, this area shaded in orange. Now, once again, there's a number of easier ways to figure out what that probability or that area would be just directly, but I'm just going to use the table that you guys all have available. Now, remember, the standard normal distribution is symmetric, right? So, basically, of course, we know the area over here is 0.5, and the area between 0 and negative 2.25 is identical to the area between 0 and positive 2.25. So first thing I want to do is I'm going to figure out the area between 0 and negative 2.25, or this part right here. And to do that, I look it up on our table right here. We have 2.25, and we end up with 0.4878. So I'll write down 0.4878. So, draw a line over here. That area that we're actually interested in then is, of course, the area to the left of a z-value of 0, which is going to be 0.5 again. Then subtract out this whole chunk that we're not interested in, which we found out was 0.4878. And that comes out to be 0.0122. So again, that represents the probability of getting a z-value that is, in this case, less than or equal to, because more extreme in this case would be less than 2.25, or negative 2.25, is equal to 0.0122. And there we got it. All right, next up we're going to check out another example where we actually perform a hypothesis test. We're going to check out 9.1.5, which is the second problem from your 12th homework assignment. The problem reads, consider the hypothesis shown below, given that you got a sample mean of 118, population standard deviation of 25, sample size was 49, and significance level of 0.1. All right. You guys may have noticed that on the page for this week, I basically gave you 5 general steps that should help you with hypothesis testing. And what I'm going to do for these examples is I'm going to follow those 5 steps for hypothesis testing, And then basically after you follow those 5 steps for hypothesis testing, you can go back and answer any of the questions they're going to ask you on the MyStatLab. Alright, so let's go ahead and start off. Step number 1 for hypothesis testing is to determine what you would like to show or prove. You just basically want to set up your null and alternative hypotheses. Now, in this situation, they already gave us our null and alternative hypotheses. The null hypothesis says that the population mean is equal to 127. The alternative hypothesis says the population mean is not equal to 127. So step number 1, we already have taken care of. Step number 2 is specify a significance level. Usually it's 10% or 0.1, 5% or 0.05, 1% or 0.01. In this case, our significance level was specified as 0.1 or 10%. So I guess I'll write that again. Oh, that's backwards. All right, step number 3 is to calculate your critical z-values and identify the region of rejection. And this is strictly based on our significance level. So now, first thing we want to think about is our null and alternative hypotheses. If these are equal to, not equal to, that means we have a two-tailed test because we're worried about it being either less than 127 or greater than 127. When you have greater than, less than type of test, then it's going to be a one-tailed test. Alright, so because we know it's a two-tailed test and our level of significance is 0.1 or 10%, that means each of our tails is going to contain 0.05 or 5% of the area, right? So 0.05 there, 0.05 there. And then that's how we figure out what our rejection region is. So now you go back to your standard normal distribution table and you want to figure out the z-value that corresponds with 0.05 of the area to the right and 0.05 of the area to the left. Basically, well, because the standard normal distribution table that we've been using only gives you values between 0 and a positive z-value, basically the value you want to look up then would be 0.5, subtract out the 0.05 you want left over, or you'd want to look up 0.450. Now, you can't find 0.450 exactly in the standard normal distribution table. You would either get 1.64 if you round it down, 1.645 if you figured out the exact value, or 1.65 if you round it up, basically. On the MyStatLab homework, and definitely on the exam, you could use any of those z-values and you'll still get the correct answer. Alright, so our z-critical values then are 1.64, yeah, we'll just use 1.64. Any of them work. So now, basically the idea is that if our test statistic falls farther away from the mean than that 1.645, then we're going to be able to reject the null hypothesis and accept the alternative hypothesis that it's not equal to 127. Alright, so again, step number 3 was just identifying these rejection regions, right? And we got those as, well, positive 1.645, and then those should all be negative values, of course. Step number 4 is calculate the z-value of your test statistic. And of course, that's just based on your sample data. Your z-value, as you know, is just your sample mean minus the population mean divided by the population standard deviation over the square root of the sample size. Of course, our sample mean was 118. Our hypothesized population mean is 127. and that's all divided by our population standard deviation of 25, divided by the square root of the sample size, and our sample size was 49. So the z-value of our test statistic is negative 2.25. Oh no, sorry, negative 2.52. We'll call that our z test statistic. That should make sense, right? Because, of course, the value of 118 is well below 127, so it makes sense we would have a negative z-value, right? Because it's below our hypothesized mean. All right, now finally, for step number 5, we just want to make a decision based on where our z-test statistic falls, whether it falls in one of the rejection regions. So now we look, of course, negative 2.52 would be somewhere about right here. So now, of course, that is more extreme or farther away from the mean than our critical value of negative 1.64, which means it does fall in the rejection region. So if it falls in the rejection region, our decision then is to reject the null hypothesis and accept the alternative. So that means at the 10% significance level, there is statistical significance evidence to show that the population mean is not equal to 127. And fun. Alrighty, let's go ahead and check out another example of hypothesis testing. We're going to check out now 9.1.8, which is number 4 from your 12th homework assignment. It reads, consider the following hypothesis test with a sample size of 22, a sample standard deviation of 8.5, a sample mean of 60.6, and then the hypothesis test we're asked to test is, the null is that the mean is equal to 57, and then of course the alternative would be that the mean is not equal to 57. And we're told to test this hypothesis at the 5% or 0.05 significance level. Alright, so once again, we're going to go ahead and follow those 5 steps I've outlined for you guys, and then after we do that, it's pretty easy to go back and answer the questions they actually asked you. Alright, so once again, step number 1 is just determine what you would like to show or prove. This means just setting up your null and alternative hypothesis. And again, in this example, they already created those for us. So that's step number 1 right there. Just creating the null and alternative hypotheses. Because sometimes they give you a situation in terms of a problem statement, and we'll look at that here in a little while, and you basically have to create your own null and alternative hypotheses. Next step is we just want to specify a significance level. I think always in this class they'll specify a significance level for you, but of course we just want to identify it. So step number 2 is just identifying this. Now, we're looking at a significance level of 0.05. So the last one was 0.1 or 10%, which was twice as much as this. So basically on that last example, we were twice as, we were let me stop there. I'll explain that later. All right, let's go ahead and go on to step number 3. Step number 3. Step number 3 says calculate your critical value and identify your rejection region. Now, on the generalized steps that I outlined for you, it says calculate your critical z-value. But in this case, since we don't have a population standard deviation, we're given a sample standard deviation. Instead of being a critical z-value, it's just a critical t-value. And again, that's just because we don't know the population standard deviation. All right. So again, I'm going to go ahead and draw the standard normal distribution. That way you can kind of see what's going on visually. Just by the way, after you guys get these processes down, problems like this only take probably 10-15 seconds. You don't have to draw all this after you get it all figured out. All right, so once again, this critical t-value in this case is just based on your significance level. Now, once again, because our null hypothesis is equal to, alternative is not equal to, we're worried about getting values either greater than or less than, so it's going to be a two-tailed test again. So now, our area of 0.05, again, is split between the two tails. So each tail is going to have an area of 0.025. But honestly, too, you can just look it up directly from your t-distribution table. Your sample size is 22, so your degrees of freedom is 21, and then you just look it up based on confidence level, 95%, because 100 or 1 minus 0.05 would be 95%, and you go down to the 21, and you end up with t-critical values of what was it? 2.0796. Now, of course, since this distribution is symmetric and it's a two-tailed test, you're going to have one critical value at positive 2.0796. And then also you're going to have a t-value or t-critical value at negative 2.0796. And once again, that helps you identify what the rejection region is. So you're going to reject the null hypothesis and accept the alternative. Basically, if you get a t-test statistic that's more extreme than 2.079 or more extreme than negative 2.0796. And more extreme again just means farther away from the mean. So again, if we want to think about this in terms of rejection regions, this is going to be one rejection region. This is going to be another rejection region. So, looks like that's all for step number 3. Moving on along, Step number 4, well, the general steps tell you to calculate the z critical or the z value for your test statistic, and this case though it's going to be a t value. So and your formula of course says that your t value is equal to your sample mean, subtract out your population mean, divided by your sample standard deviation, divided by the square root of the sample size. Our sample mean was 60.6. Subtract out our hypothesized sample mean, or sorry, our hypothesized population mean, 57. Then all divided by our sample standard deviation of 8.5, divided by the square root of the sample size. In this case it was 22. And, well, makes sense, we're going to get a positive t-value because our sample mean was higher than the hypothesized population mean, and it came out to be 1.987. Now, all that we have to do is we just look where our t-value falls in relation to these rejection regions. And in our case, our t-value, let's get a different color here, is going to fall just to the right of positive 2. Then step number 5 just says, make a decision based on whether your, well in this case, t-value fell within the rejection region. So clearly, 1.987 is not quite into the rejection region. That starts at 2.0796, right? So finally, step number 5, because it doesn't fall into the rejection region, we just fail to reject the null hypothesis. So what that means is that at the 5% significance level, there is not enough evidence to show that the population mean is not equal to 57. Then real quick, let me go over the actual questions they ask you on your guys' homework. Part A, they say, state the decision rule in terms of critical values of the test statistic. And the answer is just reject the null hypothesis if the calculated values of the test statistic are less than the negative 2.08, right? Or greater than the positive 2.08. Make sense? Part B, state the calculated value of the test statistic. Of course, our test statistic right there, we got 1.987. Step number 3, state the conclusion. Do not reject the null hypothesis. There is not sufficient evidence that the mean is not equal to 57. Alright, actually on second thoughts, I decided I wanted to talk just a little bit more about this problem, and we'll talk about something a little bit, or the significance level basically to make sure you're understanding things. So the significance level right here, 0.05, is basically the probability that you're going to make the incorrect decision. So a significance level of 0.05 correlates with being 95% sure that your decision is correct. Now, I'm going to go through and redo this problem with a significance level of 0.10. So then, instead of being comfortable with being incorrect 5% of the time, I'm basically comfortable with being incorrect twice that much, or 10% of the time. So now I'm only going to be 90% sure that I'm making the correct decision. So since I'm going to be less sure that I'm making the correct decision, it might change the results, right? So let's go through the steps again. Of course, step number 1, the hypotheses, same thing. Step number 2, now we have a different significance level. Now, step number 3, where we identify the critical values, now, instead of having 0.025 in each of the tails, we're going to have half of 0.1, or we would have 0.05 in each of the tails. So of course that means if there's more area in the tails, our critical value is going to move in. And of course, you can just look up from your t-distribution, you just look up confidence level for 2 tails, 0.1, you go down to sample size is 22, so you go to 21 degrees of freedom, and you end up with t critical values of 1.72. So we'll put that down here. We'll call this our new t critical. And of course that one's going to be negative 1.7207 to be technically correct. And then of course we're going to have another positive one over here at our other new t critical of positive 1.7207. So now, basically, our area of rejection got a little bit larger now. Everything to the left of our new critical values is the region of rejection. So now, step number 4, calculating out your test statistic. Nothing changes, right? It's still going to be 1.987. Now, the 1.987 now, look, it falls within the rejection region, so that would change our final conclusion. If we tested this hypothesis at the 0.1 or 10% significance level, we actually would reject the null alternative hypothesis and accept the alternative that the population mean is not equal to 57.